Okay, thank you very much for your kind introduction. And so, hello everybody. So, I'm Masakiyo, and first of all, I thank the organizers for organizing this workshop. So, it's my pleasure to see you online. And also, I thank you for your kind invitation. So, today, I'd like to talk about energy momentum tensor on the lattice, especially focusing on our recent study to carry out the numerical analysis of the energy momentum tensor using the so-called gradient flow. Okay, and I think we do not need much words to motivate why we should study the energy momentum tensor. Now I abbreviate energy momentum tensor as EMT. Anyway, energy momentum tensor is one of the most fundamental quantities in physics. It's fundamental because it is related to space-time symmetry, and also it appears in various fundamental equations such as Einstein equation or the hydrodynamic equations. And also, all components in the EMT is fundamental. So T00 corresponds to energy, and this part corresponds to momentum density, and spatial components and the diagonal part corresponds to pressure in thermal medium, and this all spatial part is called the stress tensor, which will play the central role in my latter part of my talk. Okay, so in this way, the energy momentum tensor is fundamental and important quantities. However, if we want to measure and define and measure the EMT on the lattice, it's actually highly non-trivial. And there are basically two reasons behind this difficulty. First one is that the definition of the EMT operator itself is highly non-trivial. This is because the space-time translational symmetry is broken by the lattice linearization. As you know, EMT is defined by as a nature current associated with the translational symmetry, but this symmetry is explicitly broken on the lattice field theory. And as a result, the naive definition of EMT, something like this, does not reproduce the correct continuum limit. And as a second problem, even if you succeeded in defining the EMT, its measurement is extremely noisy. In particular, when you want to calculate the correlation function, then more than million configurations are required. So in this way, the analysis of the EMT on the lattice is actually not easy. However, of course, EMT is a fundamental quantity in physics, and if we have EMT, there are many applications. First one is the thermodynamics. So of course, the analysis of the thermodynamics on the lattice is well established. But if we have the EMT, thermodynamics can be measured by just taking the expectation values of their components in this way. And also, the correlation and fluctuations of EMT is connected to many important quantities in physics. One example is, of course, the viscosity. That is a very important quantity in understanding the heavy ion physics. And also, the fluctuation of the energy is related to the specific heat. And similarly, fluctuation of various channels are connected to thermodynamic quantities. So this is another interesting application. And also, the EMT would be successfully used for the analysis of the hadron structure. For example, the analysis of the flux tube or hadrons itself. Then we would see the stress and pressure and energy density structure of the hadrons directly by lattice simulations. That's an interesting application. And also EMT would be successfully used for the understanding the vacuum structure. So in this way, there are many applications of the EMT on the lattice. So this slide is the contents of my talk. So in the first part, I introduce a definition of the EMT. And as Sayantan said, we make use of the gradient flow to define the EMT on the lattice. So, and then this second to six parts are the application of this EMT operator for various systems. Okay, so to construct the EMT, we use the so-called gradient flow. So let me explain what is gradient flow. And the gradient flow is a continuous transformation of the gauge field according to this differential equation. So this T is a parameter called flow time, and it has dimension of length squared. So this is not the time, but a parameter appearing in this gradient flow equation. So please do not confuse this T and real time. Okay, and then the meaning of the gradient flow becomes clear if you take the leading or tree-level part of this equation, and then the right-hand side becomes this one. So this one means that this gradient flow equation is actually a kind of diffusion equation. Okay, diffusion equation in four-dimensional Euclidean space, and this parameter T acts as the magnitude of the smearing or the smoothing distance. And actually, the diffusion distance, if we define it as a mean square radius, it is given by square root 8 times T. Okay, so in this way, the gradient flow is very simple. But this concept was introduced in the lattice community some 10 years ago. So this is because smearing and the gauge invariance is very difficult to match. So because local gauge invariance is broken by the spatial integral. So there was some invention, and before that, the smearing was performed by discrete transformation. But gradient flow performs continuously this transformation, and then many interesting mathematical property was found, especially by Lucia and Weiss. And one of the important findings is that all observables, all composite observables at positive flow time is finite. They do not have UV divergence. So this is one of the very important property. And now the gradient flow is applied to various purposes in lattice simulations. And in my talk, I make use of this concept to define the EMT operator. So to define the EMT, we make use of the assertion called the small flow time expansion. So in this argument, we consider an operator at non-zero flow time. So this is a cartoon of the four-dimensional Euclidean space, and this is the time direction. And then we consider the operator at positive flow time, non-zero flow time here. Then small flow time expansion asserts that this operator can be given by the superposition of the operators in the four-dimensional Euclidean space. So operator here. So this is the small flow time expansion. And to understand this expansion, you may imagine the operator product expansion in field theory. In the OPE, we consider the non-local operator, and we assert that it can be given by the superposition of local operators. So similarly to that, and in the OPE, there appears the Wilson coefficient, and this CI corresponds to the Wilson coefficient, and this quantity can be calculated perturbatively. So, okay. And in order to construct the EMT, we consider these two operators as a operator on the left-hand side. So they look like energy momentum tensor, but they are not because they are operators at non-zero flow time. Then we consider the small flow time expansion of these two operators. Then there appears a constant, and also next one is energy momentum tensor, because energy momentum tensor is the lowest dimensional operator, which is gauge invariant. Then as a higher order term, there would exist higher dimensional operators, but from the dimensional argument, we argue that they are order T. So in the small flow time limit, they are neglected. Okay, then by inversely solving these two equations, we obtain the energy momentum tensor in this way. Okay, so the point is that we should calculate these perturbative coefficients C1 and C2, and we also need the small flow time extrapolation to obtain the energy momentum tensor. But this definition is correct in the sense that this energy momentum tensor is correctly renormalized in the Euclidean theory. Okay, and in the following, we call this method to define the energy momentum tensor as SFtX method, as an abbreviation of small flow time expansion. Okay, and then the perturbative coefficient appearing here and here are now calculated up to 2-loop and 3-loop orders in these references. So we can make use of these parameters in the numerical analysis. And in this slide, I explain how to understand this SFtX method intuitively. So as I said, the direct definition of T mu nu on the lattice is difficult. Then we apply the gradient flow. Then we come to the smeared world. Then here we measure these two operators. Okay, and in the smeared world, if the smearing distance is significantly larger than the lattice spacing, then this system forgets the existence of the lattice spacing. And an important point here is that when we start from the continuum theory and then we apply the gradient flow, we come to the same smeared world. That is the property of the gradient flow. And then we know the connection between this continuum theory and this smeared world by the small flow time expansion. Then this quantity and these operators are connected by some analytic relation based on perturbation theory. Then by performing this quantity on the lattice and using this relation, we can reconstruct the correctly renormalized energy momentum tensor in the continuum theory. So in this argument, there are some caveats. First of all, we have to take the double extrapolation to small t and small lattice spacing. And then the flow time t is sufficiently large so that the smearing distance is significantly larger than the lattice spacing. On the other hand, flow time should be sufficiently small to suppress the effect of the higher order dimensional operators and also to justify the use of the perturbation theory. So there should exist a window of flow time to justify both these two requirements. And I will show you later in numerical analysis, actually such window exists and we can take the extrapolation numerically quite successfully. Okay, and so far I discussed the gradient flow for pure gauge field, but the gradient flow can be extended to the fermions, and in this case, the gradient flow equation looks like this. So this is no longer the gradient flow. So for the case of pure gauge theory, so right-hand side was given by the gradient of the action. But here, this is not the gradient, but just a diffusion type equation. So this is the gradient, but still we call this the gradient flow, even for fermions. Yeah, so, but take care that this is actually not the gradient flow for fermions. Anyway, by defining the gradient flow in this way, again, the all quantity becomes finite at non-zero flow time after applying one field strength renormalization this way. So we need one renormalization for the case of fermions, but by applying it, we can also use the gradient flow method and define the EMT operator. And this is the definition. So for the case of QCD, number of operators is increased. It is actually 5. But anyway, we can define EMT in this way, and these perturbative coefficients are calculated in this reference. So we can make use of this quantity to define the EMT. Okay, and finally, let me give a short comment on the definition of EMT without the use of the gradient flow. So the EMT can be defined on the lattice in a conventional way, but in this case, we have to determine these renormalization coefficients, Z6, Z3, and Z1. And their analysis had been rather hard. But recently, for the pure gauge, the precise measurement is established now, and quite recently, the strategy to measure this field strength renormalization, even in QCD, was proposed. So the gradient EMT can be measured in this method without the gradient flow. But as I discussed later, gradient flow has an advantage that it can suppress the statistical fluctuation. So okay. Anyway, now I finished the first part, the definition of the EMT. And now I come to the application part. And first one is the analysis of thermodynamics. And thermodynamics has been analyzed on the lattice so long time. So there are established methods. But in the gradient flow method, we measure the expectation value of each component in this way. So here we show the analysis of these two linear combinations. Okay, and this panel shows the behavior of these expectation values at non-zero flow time. So this axis is the flow time, and for 3 different lattice spacings. Okay, and this panel also shows the same data for E-3p. And anyway, so from this figure, you see that there is a range of t that the result behaves almost linearly. Then once finding this kind of region, we can take the extrapolation. And in this extrapolation, we need the double extrapolation. I mean, t and a has to be taken to 0. And to carry out this double extrapolation, we perform it is a very conventional method. That is, we first take the continuum extrapolation or a to 0 extrapolation with fixed flow time. And then after obtaining the continuum result, we extrapolate to the t to 0 along this axis. So let's see how to this double extrapolation is carried out. So in this figure, there is a black line here. This black line corresponds to the continuum extrapolated result for each flow time t. And then you see that this line is almost linear. Then we perform the linear extrapolation to t to 0. And this extrapolation, of course, depends on the choice of the fitting range. So we change this fitting range as shown in this range 1, 2, and 3. in order to estimate the systematic uncertainty associated with the choice of this fitting range. And then the result of the 3 fitting ranges are shown here. And you see that all result agrees within statistics. So which suggests, which shows that our extrapolation is insensitive to the choice of the fitting range. And yeah, the extrapolation is stable. And the difference of the different fitting ranges are taken into account as systematic errors. Okay, so in this way, we can measure the thermodynamics, and the result is shown here. And here, the blue points are the result obtained by our gradient flow method. On the other hand, while these lines and other points shows the result obtained by the integral method or other recently proposed methods. So you see that these results agree quite well. The error is 1% level, and all results agrees within this 1% level. So now we can measure the thermodynamic quantity quite accurately, and it's amazing that different methods agrees well. Of course, it should agree, but still it's amazing because the method is completely different. Okay, anyway. This is the result obtained for 2+1 QCD. And I again show E plus P and E minus 3P. And these panels compare the thermodynamics obtained by conventional integral method, and the blue one corresponds to the gradient flow methods. So you see that these two methods agree well in this case, and the statistical error is more suppressed for the gradient flow method. By the way, this simulation is carried out on the same configurations. So yeah, okay. And unfortunately, the quark mass is rather heavier than the physical one, but we are now performing the simulation with physical quark mass, which is summarized in this reference. Okay, okay. So in this way, we found that the gradient flow method works quite well, and it is effective in reducing the statistical error. Then let's apply this method for various analysis. And one first example is the Casimir effect and the pressure anisotropy. Okay, so let's first recall the Casimir effect. Casimir effect is okay. The appearance of the attractive force between two conducting plates located very closely. So if we locate two conducting plates with a short distance, they appear attractive force, and we know the reason why. It comes from the quantum effects, the discretization of the momentum modes. Okay, and the existence of the attractive force shows that the stress tensor or the spatial components of the energy momentum tensor looks like this. And here we choose the coordinate system in this way. So this direction is x, and then this px becomes negative, which physically means that if we cut this space by this red surface, then this upper and lower volume elements are pulling with each other. On the other hand, this if we cut this space in this way by this blue line in this way, then left and right volume elements are pushing, and this shows that PZ is positive. Okay, so you can show these relations, and the fact that PX is negative means that there is attractive force between here and here. So attractive force is propagated in this space, and this is represented by the stress tensor in this way. And the positive pressure corresponds to positive P. So this PZ corresponds to the case of the conventional thermal system. Okay, and then let's consider to heat up this system, and then the effect of the temperature act to raise Px and Pz for a positive direction. And then this negative Px will eventually becomes positive and becomes larger. And in the high temperature limit, Px and Pz degenerates. Okay, and to understand this problem, I note that there are only two-dimensional quantities in this system, that is this Lx, the distance between two plates, and T, the temperature. Okay, so all dimensionless quantities in this system can be represented by the combination of this Lxt. Okay, then now let us consider the ratio of the pressure. Okay, this Px over Pz. Okay, and then this quantity is given only by a function of Lxt, as I said. And when this Lxt is extremely large, then that corresponds to the high temperature limit or the infinitely large system. So this ratio should approach 1 unity. But as this quantity becomes smaller, this quantity becomes smaller, and eventually becomes negative around Lxt is 1.5, which means that this Px becomes negative here, and then it goes down and becomes -1 exactly here, and then finally it goes to -3. Anyway, so by the way, now in the following, I consider the periodic boundary condition along x direction, because numerical simulation is most conveniently performed with the periodic boundary conditions. And this green line is the free scalar result. Okay, then let's see what happens in the Yang-Mills theory. And the numerical result is shown here. Okay, and here I show the result for temperature slightly above Tc, 1.12 Tc to 2.1 Tc. And unfortunately, the continuum extrapolation is not taken, but the result with different lattice spacings almost degenerated, which suggests that the lattice spacing effect is well suppressed on these lattices. So anyway, from this figure, you see that this ratio is consistent with 1 here. So I think this is a very surprising result, because in the free scalar theory, this ratio becomes 0 around here, which means that Px changes its sign from positive to negative. But still, this ratio is 1. In other words, this system does not feel the existence of the boundary, or this medium near Tc is remarkably insensitive to finite size and finite boundary effect. So, and then this ratio, suddenly becomes negative. So I think this is a very strange result, and I will be happy if some of you give me the answer to how to understand this peculiar behavior. Okay, and one of the possible answer would be the effect of the non-zero quartz particle mass of gluons, for example. So because this solid line is obtained with massless free boson theory, then so I show the result with massive free boson theory result here and here. Then you see that even if the quartz particle mass is 6T, this dotted line cannot reproduce the lattice result. So still this result is strange. And this is the individual components, but I skip this slide. right? And another question is what happens in the high temperature limit? So in the high temperature limit, and because of the asymptotic freedom, the lattice data should approach the green solid line. So can we see this behavior? But unfortunately, to perform the lattice simulation, the analysis of high temperature simulation is difficult because of two reasons. One is the vacuum subtraction, and the another reason is that lattice spacing, the scale is not known. So in order to avoid these two problems, we slightly modify the ratio in this way. Here, delta is the trace of the energy momentum tensor. So this is the ratio of the traceless part of the px and pz. And then we can calculate this quantity without vacuum subtraction nor the scale setting. And the result is shown here. And on this left panel, I show the temperature result for these temperature. So this 1.68 and 2.10 was shown in the previous plot. So it is almost unity at 1. LXT is 1.5. But as temperature is raised to 2.78 and 25 TC, then you see this quantity, this ratio is gradually decreasing and approaches this asymptotic line. So yeah, the lattice data suggests that this asymptotic behavior is reproduced. But still, this convergence to this asymptotic limit is very slow. And this right panel shows the temperature dependence with fixed LXT. So yeah, and asymptotic values are shown by these arrows here. So again, still, yeah, approach to the asymptotic limit is very slow. So this is an open question. And I hope some of you give me the answer how to understand these results. Okay, and as a final word of this part, I comment that in the conventional method to measure the thermodynamics, this analysis cannot be performed because in the conventional integral differential methods, then these methods relies on the thermodynamic relations like this one or this one, which is valid only in the thermodynamic limit. So this method cannot be applicable to the finite size system. But in the SFtX method, we can perform this analysis because the thermodynamic quantities are obtained by just taking the expectation values of individual components of EMT. Yeah, so this is the reason why I did this analysis. So anyway, so the SFtX or the gradient flow method is very convenient. Okay, so I finish this part and then come to the fourth part, that is the EMT correlation functions. Okay, and there are a lot of motivations to study the correlation functions of energy momentum tensor. One of them, and maybe most interesting one, is of course the viscosity. So viscosity is obtained by the Kubo formula through this correlation function of the energy momentum tensor. And there are several motivations to study the EMT correlator. One of them is the energy and momentum conservation. Okay, because energy and total energy and total momentum are conserved. So it means that this correlator, which includes 1, 0 in the indices, should vanish. Should be tau independent constant because this quantity is conserved. Okay, and it is also interesting to see the fluctuation response relations. That is, fluctuation of energy is related to the specific heat, and the fluctuation of momentum. And also this correlation T11 and energy is related to entropy density through this relation. So it's interesting to confirm these relations. And in this study, we focus on these two topics because we are not brave enough to perform the analysis of viscosity. So to carry out the analysis of the viscosity, we must overcome the problem of the analytic continuation. And in my opinion, it's still a very difficult subject. Okay, and then let's see the correlation function as a function of Euclidean time. And this panel shows energy and energy correlator as a function of imaginary time. And from this figure, you see that this correlator is almost constant around here. And the statistical error becomes smaller and smaller as this panel shows the result for these flow times. And then statistical error becomes smaller as the flow time becomes larger. But this constant behavior becomes smaller as the flow time becomes larger. So this result is understood as the effect of the smearing. Okay, the gradient flow acts as a smearing. So this operator, local operator, is smeared with the radius square root of 2t. Then we measure the correlation between two points. Then this tau should be significantly larger than twice this square root of 2t. Otherwise, the correlator is contaminated by the effect of the gradient flow. So this over-smearing occurs around here. So we can perform the double extrapolation safely only around here, unfortunately. So that is one of the reasons why we gave up the analysis of the viscosity. To perform the analysis of the viscosity, we need a wider range of the correlator in the wider range of tau. But in this way, in the gradient flow method, the statistical error becomes smaller, but the range of tau which can be used safely becomes small. Okay, and this panel shows different channels as a function of tau. So you see there appears a constant here in this 4,4 and 1,1 channel, and this momentum channel, you also see the constant behaviors. And these constants should be the fluctuation of the energy or momentum and so on. So we should be able to extract the entropy density from this constant. Okay, then we now focus on the midpoint of the correlator, and we plot this correlator at midpoint as a function of flow time on this plot. Then it looks like this, and by taking the double extrapolation, we obtain some value here, and this value should be the entropy density because of this fluctuation-response relation, and entropy density is given by here by the red line. So they are consistent, and same consistency is also observed in this momentum channel. Okay, so we again confirmed the relation which should be valid. Okay, and from the energy correlator, we can extract the specific heat. And the analysis of the specific heat on the lattice is not easy. There are only a few analysis which carried out the analysis of the specific heat, and so our method is one of the new strategy to measure the specific heat, and the comparison of our result with the previous one is shown here, and they are consistent within statistics, I think. Okay, So in this way, the analysis of the correlation function can be done successfully again. So yeah, eventually we want to try the analysis of the viscosity. Okay. And then I come to the fifth part that is on the flux tube. So the now the topics is slightly different. I want to talk about the system in the vacuum. But anyway, so as an introduction of this part, I would like to recall the concept of stress again. Okay, stress and stress tensor in physics is related to the force acting on the surface. So as we have already seen, the most famous example is the pressure, because in a thermal system, there is a pressure, or the force is acting on a virtual surface. And in this case, the direction of the force is always perpendicular to the this plane, or this force is parallel to the normal vector of the surface. This is a property in the thermal system, but this is not always true in general, because in elastic body or fluid, as you know very well, the direction of the force is not parallel to the direction of the normal vector. And in this case, the relation between this force and the normal vector is given by this second rank tensor. And this tensor is the stress tensor. And in the conventional definition, this sigma ij is given by minus Tij. So there is a sign difference between the spatial component of EMT and the stress tensor. So anyway, and this stress tensor is very important in understanding the concept of force. So because the concept of force was first introduced by Newton, as you know well, and he considered the gravitational force, but the force that Newton considered is the action at a distance force. That means that if there are two charged objects, then there is a force depending on the charges and the distances. But after that, Faraday found that this Newton's idea is too simple. But Faraday said that our space-time is filled by the field, and the existence of the charge distorts the space around the charge, and then this distortion propagates the force. And this idea was formulated mathematically by the Maxwell. So this is the Maxwell stress tensor. Yeah. And this represents the distortion of the system. So for example, if there is an electric field along x direction, then Maxwell stress looks like this. So this x component is negative, while y and z components are positive. This means that if we cut this system by this red surface, then upper and lower volume elements are pulling with each other. They want to shrink. While if we cut this space by this blue line, then left and right spaces are pushing with each other. Then line of the field wants to repair with each other while they want to shrink. Okay, and this feature is represented in this way. So in this plot, I show the pulling direction and the pushing direction for the case of Maxwell theory. Okay, then you see that okay, there is a spread of the field along the red line. Okay, so this is a good exercise for the undergraduate course. And a famous exercise is that to take a surface integral of the stress tensor on this midplane, then the total force is equivalent with the Coulomb force. then we make sure that the Faraday's idea is actually correct. Okay, but so far everything is clear. Everything is yeah, not strange, because this is an exercise of the undergraduate course. And the non-trivial question is, what happens if we replace these two charges with quark and an antiquark? So, and in this case, it is well known that the so-called flux tube is formed in this system. In other words, the field strength is confined into a tube-like structure. And this flux tube has been studied by many people, but in the previous studies, the flux tube was studied using the potential or action density or color electric field with some fixed gauge. So the potential does not give us microscopic information of the flux tube, and the physical meaning of action density and color electric fields are not clear. So it's interesting to perform this system, to perform the analysis of this system using the energy momentum tensor. And the result is shown here. So here again, I show the pulling and pushing, so principal directions of the stress tensor. Then you see that the this red line, which is along the direction of the fields, is squeezed compared with the Maxwell theory. So the comparison is shown here. This is the result obtained by the Yang-Mills theory, while this is the Maxwell theory. So difference is clarified. Okay, and this result, the stress tensor has a very definite physical meaning. So it represents the propagation of the force in the space. So I think this is a new result anyway. And then to extract physics in more detail, let us see more precisely. But this is a lattice setting, and in the following, I show numerical result corresponding to the distance of these three green lines. Okay, so and in the following, I focus on the distribution of EMT on the mid plane between the two quarks. So on this red plane, and on this plane, due to the cylindrical symmetry, the EMT is diagonalized in this way. That is TRR. TRR means this radial direction, and this theta is longitudinal direction, and this Z is this q-cubar direction. Okay, and in the Maxwell theory, the absolute values of these four components are always degenerated. On the other hand, this is the result obtained by the lattice simulation on the midplane. By the way, the continuum extrapolation is taken, and the double extrapolation is taken. Okay, and first of all, you see that there is a separation between this T44TZZ and TRRT theta theta. As I said, in Maxwell theory, the four absolute values degenerated. So this separation is a result of the non-Abelian nature of the system, I guess. But another interesting feature is that this red and blue result and the green and orange result are degenerated within statistics. So this is an interesting this result is for the shortest distance in our simulation, and as R, the separation between two quarks becomes larger, the behavior changes like this one, but the degeneracy and separation behavior doesn't hardly change, even the separation becomes large. Okay. And we can say something about these behaviors from momentum conservation. Okay, in cylindrical coordinates, the momentum conservation in a static system, this equation looks like this. And this relation actually shows the equilibrium of the force acting on this volume element. Okay, and by supposing that the flux tube is infinitely long, then we can neglect this term. Then we obtain this relation, and from this momentum conservation, we conclude that TRR and T theta theta must separate. So this conclusion contradicts with the lattice result, which shows that the TRR and T theta theta degenerates. So from this discrepancy, we conclude that the assumption of the infinitely long flux tube is wrong. In other words, the effects of the boundaries are important for the flux tube, even at the distance is 0.92 Fermi. Okay, so some people analyzed the flux tube by assuming that the flux tube around this distance is infinitely long, but such an analysis is not justified. That's our conclusion obtained from the energy momentum tensor. Okay, and next I consider the comparison of the two definitions of the forces. Okay, now we have two definitions of the force. One is the force defined from the potential. We have the Q cubic potential. So by taking the R derivative, we obtain the force acting on a charge. On the other hand, now that we have the stress tensor, we take the surface integral of the stress tensor. Then we should obtain the force between two charges. And in some sense, the left definition of the force corresponds to the Newtonian definition, while the right definition is Faraday's local interaction. Okay, and the comparison between these two forces are shown here. This black line shows the force obtained from the derivative of the potential, while this blue point shows the force obtained by the surface integral of the stress. Then, yeah, as you see, two forces agree well. So, yeah, this is again a good result. Okay, and then we further studied this stress tensor by employing a model. So we consider the dual superconductor picture, and then we studied the Abelian-Higgs model, and we constructed the magnetic vortex in the classical theory, and then we calculated the energy momentum tensor. And in this theory, there are two parameters, and one important parameter is the Ginzburg-Landau parameter, represented by kappa. And this, depending on the value of kappa, the superconductivity or the vacuum is classified into type 1 or type 2. So, and so some people discussed the type of the QCD vacuum by comparing this Abelian-Higgs vortex and the lattice result on the flux tube. But now we can we can make this comparison in terms of the energy momentum tensor. Okay, then in the Bogomolny's bound, which is the boundary between type 1 and type 2, TRR and T theta theta vanishes. So this result is inconsistent with lattice 1. And here we assumed infinitely long flux tube. And then for the case of type 1, four channels behave like this. And for the case of type 2, yeah, result is here. So the type 1 result has positive TRR. So one may say this behavior of TRR is consistent with this lattice result. But unfortunately, T theta theta behaves something like this. It becomes negative. So this result is inconsistent with lattice 1. And actually, as I discussed already, only from the momentum conservation, we can conclude that TRR and T theta theta must separate if in the infinitely long flux tube. So yeah, we have to introduce the effect of the finite length flux tube. And then, so we calculated the EMT distribution of the magnetic vortex with finite length. Then, as shown here, we could obtain the degeneracy between TRR and T theta theta by tuning the parameters. But we found that quantitatively, all parameters are rejected. All parameters cannot reproduce the lattice data. So the naive comparison between Abelian-Higgs and the lattice flux tube is is not justified. That's our conclusion. Okay, and yeah, using last 3 minutes, I come to the last part, the single quark system at non-zero temperature. Okay, so far I considered the Q-Cuba system, but yeah, it's interesting to consider the system with a single quark. Okay, by putting a single quark in the vacuum, yeah, the fields system are distorted, and this system has non-zero energy momentum tensor. Of course, this setting of the system is prohibited with a finite volume in the vacuum. But in the deconfined phase, we can consider this situation. And the motivation to study this system is the connection to the recent progress on the analysis of the EMT distribution inside hadrons. So now some people argue that they have succeeded in the measurement of EMT distribution, pressure distribution inside hadrons. So they are related to EMT form factor or the gravitational form factors and so on. So yeah, okay. So if we succeeded in perform the same analysis in full QCD, then the single quark system corresponds to the heavy light meson. So that is one of our future work. But here we consider the pure gauge theory, and we put the Polyakov loop at the origin and calculate the EMT distribution around it. And in the we have to consider the deconfined phase, because when the Z3 center symmetry is not broken, this quantity becomes 0 over 0. So it's not defined. So yeah, we fix the one of the Z3 minima in our simulation. Okay, and then to study this system, we should employ the spherical coordinate system. And yeah, in the spherical coordinate system, the EMT is diagonalized in this way: one longitudinal component and two transverse components. And in the Maxwell theory, these three components looks like this. Okay, and the numerical result is shown here. This left panel shows the same plot as the flux tube. So red and blue line corresponds to the pulling and pushing directions. And this right-hand side shows the R dependence of the three channels of the EMT. And you see the separation of the three channels here. So this is again the feature which is not observed in the Maxwell theory. Okay, and in this panel, I show the TRR in this representation. Okay, and this R is physical distance, and here I show the result for 4 temperatures. Okay, and you see this and at the leading order perturbation, these 3 quantities should behave like this. So we would extract alpha s for small distances and the device cleaning mass at large distances. But unfortunately, the error becomes large, and we gave up the analysis of the screening mass. Okay, and but we still are able to extract the running coupling. from this behavior, and we employed this relation, which is valid at the leading order perturbation theory, and then we extract alpha s as a function of R, and it behaves like something like this. And so finally, I comment that this result is consistent, qualitatively consistent with the estimate of the running coupling obtained from the Q-cuba potential done by Kaczmarek, Karsh, and Zanto. Okay, so now I come to the summary. So now successful analysis of EMT is available, is possible. Yeah, and various studies are ongoing. Okay, and yeah, so and in particular, the gradient flow or SFtX method works quite well. And yeah, I discussed various applications. But yeah, as a future study, I should say that there still are many applications, because energy momentum tensor is one of the most fundamental quantities in physics, especially the analysis of the flux tube at non-zero temperature and EMT distribution inside hadrons and viscosity and other operator other than EMT. And yeah, and the analysis through QCD are also interesting. Okay, thank you very much.
Thanks, Masakiyo, for this wonderful talk. And questions, please. So I see question by Ayan. And please go ahead.
Hi, Masakiyo. Thanks for the wonderful talk. I have a very naive question, actually. It's about your slide 18. And you also mentioned something on slides 36, but it's about slide 18, actually. So I think you showed that if you evolve in T, there comes, yes. No, the slide before that. Yes, yes. So if you look at very small t, it doesn't look like a linear behavior, whereas only in after some delay, the linear behavior arises. So is it not in contradiction with this perturbative theory, or do you expect this linear behavior to come without delay only in the continuum limit?
Okay, so the deviation around here is interpreted as the lattice artifact. Okay, and actually, as the lattice spacing becomes finer, this suppression becomes weaker. Okay.
So in the continuum limit, it will be coming without delay. The linear behavior comes without delay in the continuum limit.
Yes, yes, exactly.
And there was some statement that you made on slide 36 about, so practically you could get this linear behavior only in a very short range of t, and that was the problem of why is this related to this issue that of taking the continuum limit could be hard, or what exactly is the issue here?
Okay, so yeah, okay, so so how to answer? So yeah, to justify this method, so we assume that the operators are isolated. So this gradient small flow time expansion is can be justified only for local operators. So in other words, the operators has to be separated. Otherwise, if there is an effect of the over smearing, then there appears an overlap between two operators. Then the use of the small flow time expansion is no longer justified. Then, yeah, we took the linear extrapolation, but this linear extrapolation appears as a result of the small flow time expansion. But when the two operators overlaps, the SFtX is violated. Then, yeah, we can no longer perform the linear extrapolation. Do I answer to your question?
Yes, indeed. So, but this will not be happening if they're well separated, if the two operators are well separated.
Yes.
Okay. Thank you. Thanks.
Thank you.
There is a comment by Paul. Paul, do you want to ask yourself or make this?
Yeah, sure. I can easily ask the question or do the comment. So basically, it is just a suggestion that I think these are very nice methods that you have here. Maybe would you be able to sort of revisit some of these old calculations of these so-called thermodynamic transport coefficients? There's in particular this paper by Owe Philipsons and collaborator that I indicate in the chat, where they look at the Euclidean correlator, and basically what you have to do is you don't have to do an analytic continuation, you just have to do an extrapolation to Q is 0 to get the derivative of the correlator to extract this transport coefficient. So now that you have a sort of very powerful method to get Euclidean correlators, I think it would be interesting to revisit those results from 2013.
Okay, so their argument is that there is some relation between transport coefficient, which does not depends on the Kubo formula, right?
No, this is a Kubo formula. It's just a different Kubo formula from the viscosity. It's second order.
Okay. I see. Okay. Thank you for your comment. Yeah, I think it's interesting.
I see no question. I quickly wanted to ask a question. So for the fermionic operators, suppose psi bar psi, will this be a problem that when you use nearing of the fields psi and psi bar, then this operator will also have the same problem that it will not have a peak-like structure or a flat plateau-like structure?
Sorry, I couldn't listen to you. Could you explain again?
Yeah, for the chiral condensate, if you want to look at these kind of operators, yeah. So these are also local operators.
Yes.
So will there be a issue with the flow for these operators, or is it fine? Or like correlators of the chiral condensate?
So you are interested in the analysis of chiral condensate with the gradient flow?
Yeah, or is correlators? Yeah.
Yes.
Do they have like plateau-like structure, very prominent plateau-like structure as a function of flow time, or these operators also have issues that they don't have a stable plateau?
Yeah, actually, yeah, we are performing the chiral condensate, performing the analysis of the chiral condensate and its correlation function now.
Okay.
Yeah, so yeah, we can define any local observable using the small flow time expansion. So yeah, chiral condensate can be defined in this method. And yeah, we are doing that analysis. Okay.
Okay, thanks. I see no further questions here in the chat box. So thanks a lot again, Masakiyo, for the talk. And